Hi, everyone. This is Dr. Hammett, and Dr. Fry had asked me to, or actually all of us, to make a commercial for our capstone. Um, some people are giving those in person. I just decided to do mine in video format, and here it is. So my capstone is called Combinatorial Game Theory, and in order to take it, you would need to take graph theory and combinatorics, and really just any course in probability at all. And I just want to spend some time talking about the specifics about what might go on in this course and what these words even mean in the title of the course itself. So what's combinatorics? Well, that's an interesting question. Sometimes if you want to stump a mathematician who happens to be a specialist, just ask them to define the area in which they work. That can be a little bit tricky sometimes, and actually asking my own self this question got a little bit tricky, but here's the best way I can describe it. Notice that this word combinatorics has combine, looks like it's combine torics, right? And in essence, what you do in combinatorics is you essentially look at various collections of mathematical objects that are built from similar structures, and you might be interested in counting them or combining them in some way or asking questions about them. So for instance, if I gave you like 3 points like this and 3 lines that you could put between those points, oftentimes we call those points vertices and those lines edges. How many ways could you draw points and lines joining those points, therefore creating something that combinatorialists call a graph? Well, there's kind of the silly graph that doesn't have anything. There's a single point graph. There's a graph that happens to have 2 vertices and no edges. You kind of have a silly 3 vertex graph and no edges. You can kind of have a single edge joining 2 points, okay? You could kind of have a single edge joining 2 points and then 1 point off like this. You could have 2 edges joining 2 points like this. And you could have this as well. Okay, so I would say that combinatorics, I think that's everything that I've listed here. There's also things you could do. I could even put labels on those vertices, and then you might get more options when you do that. You would have to think that through. But combinatorics is basically the study of mathematical objects created from substructures that most of the time you can list and think about and discern various properties within them. So the second part of the title was game theory, right? So combinatorial game theory. So what's game theory? Well, in game theory, typically you have 2 players that are playing some kind of game. And the question is, what is the optimal strategy one would have to deploy in order to win the game, or like guarantee that they're going to win the game in some way? And the reason I use the term combinatorial is there are certain games you play that involve combinatorial objects, like what I just described before. So I thought the best way to illustrate that would be to actually play a game. And I have my son here with me, Daniel, and he's going to play a pretty famous game with me that kind of falls directly into the category of a combinatorial game. So we are 2 players, myself and my son Daniel, and we're going to play a little game for you to kind of get a flavor for this. So here's the game. Here are a bunch of dots, okay? I'm going to call these pearls, okay? And you'll know why in just a minute. So there's 8, 9, 10, 11, 12. So there's a total of 12 pearls here. And Daniel and I are going to play. And the rules are, on our turn, we get to take 1 or 2 pearls. 1 or 2 pearls, okay? And the winner is the one who kind of exhausts the pile. So the last person that actually takes and finishes the pile ends up being the winner. So if I can create a situation where I'm the last one to take a pearl, I'm the winner, okay? And so what I'm trying to do to my opponent, Daniel in this case, is to prevent him from even having the opportunity of taking the last pearl and exhausting the pile. So describing a strategy for this game would involve trying to think through, okay, do I want to go first? Do I want to go second? Is there something I should be doing on every turn to ensure that I win the game? So all of these things are questions that we would be trying to answer, and you would have to think through some interesting combinatorics along the way. So Daniel's going to help me. Daniel, do you want to go first, or do you want me to go first? Say it.
You.
Okay, you want me to go first. Well, okay, I'm going to take one. All right, so all of mine, I'm going to kind of slash off with a vertical slash. Okay, Daniel, you go next. How many? You want to take two? Okay. Well, I'm going to take, I'm going to take one. What do you want to do, buddy?
One.
You want to take one? Okay. I'm going to take one. Okay. What do you want to do, bud?
One.
You're going to take one. All right. I'm going to take one. Actually, no, I'm going to take two. Okay, what do you want to do?
I'm going to take
What do you realize is going to happen, buddy?
You're going to win.
Well, okay, you want to take two?
Yeah.
Okay, so if you take two, I'm going to win by taking one. But if you would have taken one, I would have taken the last two. See what I'm saying? So this game belongs in a class of games called NIM type combinatorial games. And they're pretty famous. This is one basic version of a NIM type game where we put an upper bound on the number of pearls you can take at a given time. We're playing with one pile. There are variations of NIM where you don't put upper bounds on the number of pearls you can take at a given time. You might have multiple piles and you can only take from one pile at a time, for instance. And you might actually change up the game itself and say, okay, the winner isn't the one that takes the last pearl. The winner is the one that forces the other player to take the last pearl, okay? So that is called a NIM type game, and that would be exactly the sort of thing we'd be interested in, trying to strategize about whether to go first or second, what the strategy is that we would deploy, and it turns out you can do some fairly rigorous analysis of these kinds of games. All right, so pearls before swine. I want to encourage you to go check that out. There's a little iPhone app that you can play. This is actually a NIM type game, and it's a little biblical integration for you, right? Pearls before swine. You play this guy, Juan. He has some pearls in his hands that belong to several piles, if you will, and it's a NIM type game. I would encourage you to kind of strategize about that. Although I think in this version, the winner is the one that forces the other player to take the last pearl. Okay, so you have to kind of rethink your strategy in that way. I would encourage you to go mess around with that. It's interesting stuff. That's not the only kind of games that we would be interested in. I mentioned that I enjoy, or that I would prefer that you take a probability class. And indeed, I enjoy probability. It turns out that in my area of combinatorics, there's a lot of times that you have to employ probabilistic strategies. That's mainly due to a pretty famous mathematician by the name of Paul Erdős, a Hungarian mathematician, who solved a lot of combinatorial problems by recasting them as probabilistic problems. And he introduced something called the probabilistic method to that end. And at that point in time, combinatorialists all became very interested in probability. So a lot of combinatorial games will involve a probabilistic analysis, or they may just be combinatorial in nature. Here's an example of one that I wrote a review for about 5 years back. It's a guessing game. It's guess the largest number game. This guy, Alexander Ganedin, is pretty well known. And I reviewed this little paper that he wrote. It's interesting. It basically has to do with a couple of numbers being chosen according to some probability distribution. And then you essentially have to decide which of the two numbers is larger, which seems kind of like a dumb game. But he introduces a strategy that involves a threshold number to help you make that decision that actually increases your chances of winning. So sometimes what you're trying to do is increase your odds of winning. And actually, I wrote a paper about 5 years back with my colleague, Greg Oman from the University of Colorado in Colorado Springs. And that's the sort of thing that we did. We analyzed a game where you start with a player A who chooses a number, and then the goal is to guess what that player A's number is. Okay, so it's not necessarily about you know, A and B winning here, although I guess you could say if I don't guess player A's number, I win, and if I don't guess player A's number, she wins, and if I do guess, then I win. And what we did is we kind of created a scenario where you're allowed to ask a sequence of yes or no questions about the number, and then you have to make a guess after some number of questions. And we came up with all possible algorithms that maximize the probability that you actually are going to correctly guess that number. And it was fairly surprising how much leniency you have in terms of posing your questions. It's a big surprise to us. We also had to compute the probability that player B actually wins. And this paper right here is a follow-up that I actually wrote with an undergraduate who's now a PhD student at Western Michigan University, where instead of yes, no questions, we changed it to like multiple choice questions about the chosen number. And it turns out that you get some interesting results there as well. So, I mean, if you have time, you could go check those out. These aren't the only kinds of games we're going to be looking at, but these are the sorts of games that fall under the umbrella of combinatorial game theory. And I hope you'll consider joining us for that capstone. That's all for now.